Hello everyone, and welcome to a video on energy around us. In this video we will be focusing on working energy. What is working energy and the different types of working energy that we can find. So firstly, we need to know what is working energy. And working energy is simply the energy that is doing work in a system. That means that it is actively causing movement or change because work is moving or changing something. So anything that is moving or changing something is using energy. So we're using one of the 5 working energies. It's like this hammer, for example, is smashing into a stack of bricks. First of all, it had to move, and once it hit the bricks, it changed the bricks because it is causing the bricks to change because it is breaking them apart. And on the right, we see a light bulb that is illuminated by electrical energy, and it is lighting up the room. So the work it is doing, it is illuminating the darkness in a room. So there are 5 different kinds of working energies. There is kinetic energy, there is thermal energy, there is sound energy, there is light energy, and there is electrical energy. So the first one we're looking at is kinetic energy. And kinetic energy is the energy of movement, right? So movement is kinetic energy, and without kinetic energy, you cannot have movement. So this ball is rolling down a slope, right? The gravitational potential is being converted into kinetic energy for the ball to roll down, and so the ball has the kinetic energy. Once more, objects that have kinetic energy can transfer their kinetic energy into another object, causing it to also have kinetic energy. If we look at this image here, we see a contraption called the Newton's Cradle. And the way it works is the first pendulum ball hits the second, third, and fourth pendulum ball, sending its kinetic energy through to the 5th pendulum ball, causing it to lift in the air and then come back down and repeat the process. So from that direction and then back to that one. So you'll notice that the second, third, and fourth are moving, but that's because they're already in contact with one another. So as soon as they get the kinetic energy, they immediately transfer to the next one and the next one. And then the 5th one and the first one aren't blocked by any other ball, so they have the freedom or the ability to move with the kinetic energy that they have gained in the system. Right, and here we have another example of what I just said about energy transfer of kinetic energy. You can see that at first the soccer ball is moving, but once it hits the poor man's face, we see that the kinetic energy that the ball had is transferred into the man's face, causing the man to move and the ball to almost stop moving entirely. Right, then we have thermal energy, which is, to our perception, what makes things feel either warm, hot, or cold. If we put our hands near a flame, we notice that the flame, it feels hot. And if we put our hands on ice or we hold ice, we notice that the ice feels cold. Thermal energy is generated through friction, right? So when things rub against one another, that generates thermal energy. And thermal energy transfers from warmer objects to colder objects. So rubbing your hands together, you'll notice that it makes you feel your hands feel warmer, and that's because you're generating friction from the movement. And this flame transfers its heat that the flame generates, the thermal energy that is generated by the flame, into the cooler metal of the pot until the pot is as warm or gets warm enough to do what it needs to do, which is to cook food. So again, if I had to show you that energy transfer, that the thermal energy from the flame will be transferred into your finger because your finger has less thermal energy than what the flame is generating. And in terms of ice, the thermal energy from your hand will be transferred into the ice because the ice has less thermal energy than your hand, causing your hand to feel colder. And that's because the thermal energy that was in your hand is being transferred into the ice, causing the ice to warm up and then melt back into a liquid state. There are 3 ways that heat is transferred, or heat can be transferred, and that is through conduction, convection, and radiation. Right, I'm not going to spend too much time on that, but that can be covered in another video. Right, so sound energy. Sound energy is the vibration of particles traveling in the form of waves. So you'll notice that these waves there's like wave pattern here, and that's what sound energy would look like. It looks like when it is recorded, right? In this, in this manner. So the height of the wave shows the energy available in the sound wave, and the length between each wave point shows the wavelength. So like shows how, like the frequency of the sound, so how fast each sound wave is moving or hitting after the next one. So the more waves there are close together, the higher pitch the sound will, or the more frequency the sound has. So it sounds more like a high-pitched sound, and if the waves are far apart, it sounds more like a low sound. But anyway, that's just actually, you don't need to know that. So this is what it looks like if we show it in this manner, but in a more realistic way, or closer to reality, this is actually you'll see that, look at the compression of particles by where the waves are, and so those particles are vibrating in a form of wave, and they are hitting your ear, or they're hitting an object, causing that to vibrate as well. So sound doesn't travel in just one direction, but it travels in every direction. And that's why someone can talk to you without facing you, and you can still hear them. Like, you don't have to look at someone to hear them, because sound travels in not just a 2D or 2-dimension, but also in a 3D dimension in every direction from the source, right, in the form of waves. So it's similar to like how ripples in water work. The source is in the middle, and then the ripples basically emit or send or like basically move out from the source in rings in every direction, and that and the further the ripples go, basically the weaker they become. And sound is like that too. The further the sound wave has to travel, the more energy it loses, the less energy it has when it reaches you. So that's why things or sounds that are further away sound softer than if you were right by them. Right, and sound is also influenced by the state of matter that a material is in. Sound moves very easily through solids because the particles are all very close together. In liquids, they also move relatively easier, but not as easy as in solids. And in gases, sound has the toughest time to travel through those particles because the particles are moving and they are far apart from another. So a lot of energy in sound energy is lost as it moves through gases like air, for example. Right, and because of that whole needing particles to vibrate for sound to travel, in space where there's nothing in between, where there's just emptiness, the sound cannot travel because there's no particles to vibrate and to move in waves. So even if you had to scream right next to your partner, they would not hear a single thing because sound cannot travel in an empty space or through a vacuum. Right, and lastly, on a side note, the ear or our ears are the only reason that we can perceive sound as sound. Otherwise, it would just be vibration. It would just be like, something vibrating, and you wouldn't hear anything. So animals that don't have ears, or living things that have no ears, like trees or plants, for example, don't hear sound, but they do still feel it. They feel vibrations, but they don't hear anything like us. Our ears actually transform. You'll see in this GIF how it transforms vibrations, using these bones, the ossicles, and hitting your nerve or your cochlea in the middle, your middle ear, and then your inner ear, and then how that converts the vibrations by sending it first to your brain, and how your brain turns vibrations into sound. So your brain is your ear and your brain is what helps you translate vibration into sound energy. Right, so light energy, this is energy. This energy is why we can see anything at all. So when you think of light energy, lots of people think of light bulb, right? Which is true, which is correct, because light bulbs do emit light energy, and it's what we use to light up our houses at night. But light energy can also come from other sources. One such source is from bioluminescence, which is light emitted from living organisms. Like, for example, these fungi this mushroom is emitting a very cool looking green light, right? And these jellyfish are also emitting a very pretty looking blue light. And usually animals or living things that live in or have bioluminescence live in very dark places where there's no light from other sources, so they generate their own bioluminescent light. But the main source of light is actually from our star, the sun, and that actually provides the most light, or most of the light in our entire solar system. So light is generated by the movement of energy particles called photons, and these are the photons. Photons aren't yellow, right? They're just made yellow in this picture so they're easier to see. Photons have no color, right? Color is also basically, it's made up by our brain, right, what color, but I'm not going to go into that now. But just know that light is actually generated by the movement of these tiny little energy particles called photons that move at the speed of light, which is the fastest you can move, and there's trillions upon trillions of them moving in any direction at once. And what that means to us with our eyes, what we see are these light rays. So it looks like solid beams of light, but it's actually trillions and trillions of tiny little particles called photons moving from the source to our, which is the sun, to our planet, and bouncing off all the different surfaces, and then eventually reaching our eyes, giving us the image of what our environment is in front of us. Which is why when there's no photons, you can't see your environment, since there's no photons bouncing off the environment into your eye. All right, so the last one we're looking at here is electrical energy, and that is generated by the movement of electrons between atoms. And if you don't know, electrons are another type of energy particle that we find floating on the outside of atomic nucleus. So this is the nucleus where the protons and neutrons are, and the electrons are basically those energy particles floating on the outside of it. In a closer look to a more realistic vision is that the electrons are orbiting around the nucleus, kind of like how the planets move around the sun, except this image doesn't show you a realistic view, because in reality the electrons are moving so fast you wouldn't actually be able to see them move. So it would just look like a lot of blurry lines around the nucleus from the speed that they're moving. So there's two types of electrical energy. The first one is static, and that's when electrons are pulled from their atoms by friction, like two things rubbing against each other, and they move to one object, leaving one of the objects with less electrons and the other object with more electrons than they started with. This means that one object, like this rag over here, will have a positive charge because it has now more protons than it has electrons, and this pipe that gains the electrons is negatively charged because it basically took the electrons from the rag, and now it has more electrons than protons, and that's why it is now negative. So basically, if I put it simple, the minuses are the electrons. Now there's more minuses on the pole after it rubbed the cloth, and now the cloth or the rag has less minuses, meaning it is positively charged, and the pipe is negatively charged. Right, and if you want to see static electricity in a practical way, this is what it would look like. So this buoy is negatively charged because it's touching this, this electrode over here, and the electrons are moving into his hair, into the atoms of his hair, causing them to become all negatively charged. And because they all have the same charge, they push each other away, so all his hair is basically trying to get away from all the other hair, making him look like a porcupine. And then the second type of electrical energy we have is electrical current, and that is when electrons flow in one direction and they move from one atom to the next in one direction, creating a current of electrons. And that is, and the way we experience this is in our electrical circuits, right? When, for example, the batteries in cells, like the electrons move from the negative side of the cell through the wire back towards the positive side, and then it repeats. So the electrons are flowing from the negative terminal of the cell to the positive terminal of the cell, and this happens until there's no more, basically the cell runs out of chemical energy. And then another way we can experience electrical current is lightning. When the electrons flow from the negatively charged clouds to the positively charged ground. So the lightning is actually, it's not the electrons you're seeing. Lightning is actually when the air gets so hot, the gas and air gets so hot from the electrons moving through it, that it starts to glow from all that thermal energy. So what you're seeing is not electrons, but what you're seeing is the work that the electrons are doing to the gases in the air. And that's what lightning is. All right, so I hope that you found that helpful. And if you did find it helpful and you would like to see more in the future, please drop a like and please subscribe to the channel. It'd be much appreciated. Stay awesome. Till next time.